I found a set of papers that better capture some of the details of climate change during the Holocene and the teleconnections from one place to the other, like greening of the Sahara to the monsoon and South America, and impact on ENSO and so on. So let's just go through them. I won't include the figures and just read the abstracts, because the figures again tend to be the typical paleo figures, which are always kind of a little bit you need the proper intuition to understand the stacked data from various sources, various isotopes, and various matchings of the different periods in different data sets and so on, and so different proxies, for example. So let's just go through these. The common author in these papers is this person, Francesco, I don't know if it's Francesco Posata. End of Green Sahara amplified mid to late Holocene megadroughts in mainland Southeast Asia. So you can imagine that there were already attempts at agriculture, and the spreading of civilizations from the Nile into the West Africa happened during Green Sahara, and then Southeast Asia was having its own cultural dynamics, response to climate and so on. So just reading the abstract, between 5 and 4,000 years ago, crippling megadroughts led to the disruption of ancient civilizations across parts of Africa and Asia. Yet the extent of these climate extremes in mainland Southeast Asia has never been defined. This is despite archaeological evidence showing a shift in human settlement patterns across the region during this period. We report evidence from stalagmite climate records indicating a major decrease of monsoon rainfall in mainland Southeast Asia during the mid to late Holocene, coincident with the African failure during the end of the Green Sahara. So Green Sahara lasted for a while, related to orbital forcing, monsoonal changes, and then it collapsed. Through a set of modeling experiments, we show that reduced vegetation and increased dust loads during the Green Sahara termination shifted the Walker circulation, which is the zonal circulation in the deep tropics. If you don't know what that is, you can look up on my podcasts on this topic elsewhere. And this cooled the Indian Ocean, which has the subsiding branch. So on the maritime continent, you have the ascending branch, you have subsiding branch on western India and in eastern tropical Pacific. Okay, so the Indian cooling then obviously had impacts on the monsoon as well. Through a set of modeling experiments, we show that reduced vegetation and increased dust loads during Green Sahara termination shifted the Walker circulation, which means the major convection center would have shifted eastward, so from the western Pacific maritime continent towards the dateline, and cooled the Indian Ocean, causing a reduction in monsoon rainfall in mainland Southeast Asia. Our results indicate that vegetation dust climate feedbacks from Sahara drying may have been the catalyst for societal shifts in Southeast Asia via ocean-atmosphere teleconnections. So you can see what happens. One place may be more sensitive to orbital forcing than other, but once that force, the place that is sensitive responds, then it can send teleconnected responses elsewhere, which are not as sensitive to orbital forcing directly, like precession cycles, at which monsoon has a strong response. The remote response of the South Asian monsoon to reduced dust emissions and Sahara greening during the middle Holocene. So this is now looking at the South Asian monsoon response to Sahara greening during the mid-Holocene. Previous studies based on multiple paleoclimate archives suggested a prominent intensification of South Asian monsoon during the mid-Holocene, so that's around 6,000 years before present. The main forcing that contributed to this intensification is related to changes in the Earth's orbital parameters, which is what I mentioned. Nonetheless, other key factors likely played important roles, including remote changes in vegetation cover and airborne dust emission. So the orbital forcing may induce a response, and then that response induces delayed or simultaneous feedbacks in the system, which create other remote responses. Nonetheless, other key factors likely played important roles, including remote changes in vegetation cover and airborne dust emission. In particular, Northern Africa also experienced much wetter conditions and a more mesic landscape than today during the mid-Holocene, which is called the African humid period, leading to large decrease in airborne dust globally. However, most modeling studies investigating the SAM changes, South Asian monsoon changes during the Holocene, overlooked the potential impacts of the vegetation and dust emission changes that took place over northern Africa. Here, we use a set of simulations for the mid-Holocene climate in which vegetation over the Sahara and reduced dust concentrations are considered. So they have a model which considers these feedbacks explicitly, even though, again, you have to be aware that dust can have direct impact in terms of affecting solar radiation, or indirect effect by changing cloud condensation, nuclei, cloud microphysics, rainfall distribution, droplet sizes, and so on. Our results show that South Asian monsoon rainfall is strongly affected by Saharan vegetation and dust concentrations, with a large increase in particular over northwestern India and a lengthening of the monsoon season. We propose that this remote influence is mediated by anomalies in the Indian Ocean sea surface temperatures and may have shaped the evolution of South Asian monsoon during the termination of the African humid period. Okay, so you can see again another teleconnection that's slightly different than the Southeast Asian change. Another indicator, the greening of Sahara, past changes and future implications. So it's the same person leading this study, kind of a review that looks at the paleoclimate during the Holocene, tries to argue what it may mean for the future. In the future, the Sahara and Sahelian region could experience more rainfall than today as a result of climate change. Wetter periods termed African humid periods occurred in the past and witnessed a mesic landscape in place of today's hyper-arid and semi-arid environment. Such large past changes raise the question of whether the near future might hold in store similar environmental transformations, particularly in view of the growing human-induced climate, land use, and land cover changes. In the last decade, geoengineering initiatives in the form of active re-greening projects of Sahara and Sahel have been proposed and could have significant effects on the climate of the region. Here, we synthesize the literature on the past and projected changes in the hydroclimate of the Sahelian-Saharan region and the associated feedbacks. We further address the current state of knowledge concerning Saharan and Sahelian afforestation projects and their consequences. Our review underscores the importance of vegetation in land-atmosphere-ocean feedback processes and far-field impacts of North African ecosystem changes. So you can read the paper, which is a nice review for the details of what they actually conclude. In the meantime, I have somebody at the door. Give me 1 second here. Okay, so sorry about that. Looking ahead, so mesic is basically a system that is humid enough for some ecosystems. It's not desert, it's not wet monsoon, but it's humid that is supporting some vegetation that are not there in the dry deserts. Initiation of a stable convective hydroclimatic regime in Central America circa 9,000 years before present. So again, Posata is one of the authors here. Okay. Many Holocene hydroclimate records show rainfall changes that vary with local orbital insolation. However, some tropical regions display rainfall evolution that differs from gradual precessional pacing, suggesting that direct rainfall forcing effects were predominantly driven by sea surface temperature thresholds or interocean temperature gradients. Here we present a 12,000-year continuous uranium-thorium dated precipitation record from a Guatemalan speleothem. So it's a cave formation that records rainfalls through groundwater and growth rates and bands in the stalactites and stalagmites and so on. So the Guatemalan speleothem showing that Central American rainfall increased within a 2,000-year period from a persistently dry state to an active convective regime at 9,000 years before present and has remained strong thereafter. Our data suggests that the Holocene evolution of Central American rainfall was driven by exceeding a temperature threshold in the nearby tropical oceans. The sensitivity of this region to slow changes in radiative forcing is thus strongly mediated by internal dynamics acting on much faster timescales. So right now you can see what is called the Western Hemisphere Warm Pool by Chunzai Wang. So there is a warm pool in the Western Atlantic Ocean in the tropics, and then the Gulf of Mexico is very warm. So this together affects the climate over South America, which is what this is talking about, and how it changed 9,000 years before present. Another work, the water cycle of the mid-Holocene West African monsoon, the role of vegetation and dust emission changes. So these feedbacks are very important, and the kind of coarse resolution simulations that we looked at for the marine isotope stages may not have always captured these feedbacks in detail, at least. Okay, so they might have represented it in a much coarser way, but using the data to infer them is always useful, plus model validations, which is typically what Posata does. During the mid-Holocene, 6 kiloyear before present, West Africa experienced a much stronger and geographically extensive monsoon than in the present day. Changes in orbital forcing, vegetation, and dust emissions from the Sahara have been identified as key factors driving this intensification. Here, we analyze how the timing, origin, and convergence of moisture fluxes contributing to the monsoonal precipitation change under a range of scenarios. Orbital forcing only, orbital and vegetation forcings, Green Sahara situation, orbital vegetation and dust forcing, so Green Sahara, reduced dust. So when the Sahara is not as green, there is a increased dust loading. When Sahara greens, the dust loading is reduced, so the combined effect will be different than just the vegetation effect. We further compare our results to a range of reconstructions of mid-Holocene precipitation from paleoclimate archives. In our simulations, the greening of the Sahara leads to a cyclonic water vapor flux anomaly over North Africa with anomalous westerlies flow, bringing a large amount of moisture into the Sahel region from the Atlantic Ocean. So cyclonic is counterclockwise, so winds coming off the warm Atlantic Ocean over to Sahel bring more moisture. Changes in atmospheric dust under a vegetated Sahara shift the anomalous moisture advection patterns northward, increasing both moisture convergence and precipitation recycling over northern Sahel and Sahara, and the associated precipitation during the boreal summer. During this season, under both the Green Sahara and Green Sahara reduced dust emission scenarios, local recycling in the Saharan domain exceeds that of the Sahel. So Sahel is the southern edge, the transition between the wet ITCZ region with Central African forests to Sahara, which is dry or green depending on the regime of climate we're talking about. This points to local recycling as an important factor modulating vegetation precipitation feedbacks and the impact of Saharan dust emissions. Our results also show that temperature and evapotranspiration over the Sahara in the mid-Holocene are close to Sahelian pre-industrial values, so all the way up to through Little Ice Age, for example. This suggests that pollen-based paleoclimate reconstructions of precipitation during the Green Sahara period are likely not biased by possible large evapotranspiration changes in the region. So vegetation feedback, you have to be sure that you are not misrepresenting any of the climate changes and climate feedbacks just by relying on pollen records. This is about tropical cyclone activity being enhanced by Sahara greening and reduced dust emissions during the African humid period. So I don't know if I want to read all of it, but maybe it's just better to read it. Tropical cyclones can have a devastating socioeconomic impacts. Understanding the nature and causes of their variability is of paramount importance for society. However, historical records of TCs are too short to fully characterize such changes, and paleosediment archives of the Holocene TC activity are temporally and geographically sparse. Thus, it is of interest to apply physical modeling to understanding TC variability under different climate conditions. Here we investigate global TC activity during a warm climate state mid-Holocene 6,000 years before present, characterized by increased boreal summer insolation, a vegetated Sahara, and reduced dust emissions. We analyze a set of sensitivity experiments in which not only solar insolation changes are varied, but also vegetation and dust concentrations. Our results show that the greening of Sahara and reduced dust loadings lead to more favorable conditions for tropical cyclone development compared with the orbital forcings alone. In particular, the strengthening of the West African monsoon induced by the Sahara greening triggers a change in atmospheric circulation that affects the entire tropics. Furthermore, whereas previous studies suggest lower TC activity despite stronger summer insolation and warmer sea surface temperatures in the northern hemisphere, accounting for the Sahara greening and reduced dust concentration leads instead to an increase in TC activity in both hemispheres, particularly over the Caribbean basin and east coast of North America. Our study highlights the importance of regional changes in land cover and dust concentrations in affecting the potential intensity and genesis of past TCs, and suggests that both factors may have appreciable influence on TC activity in a future warming climate. Okay, this is about the abrupt shift in the Indian monsoon 4,000 years ago. We have addressed this already once, but just to read it off, the emergence of high-resolution proxy records from the Asian monsoon region suggests that the monsoon system is bistable and can abruptly transition between a suppressed and active state. This observation is critical in considering how the monsoon system may have influenced the development of societies across South and East Asia during the Holocene. Using a new high-resolution, so 5-year sampling, Speleothem's stable isotope record from northeast India that spans the early and mid-Holocene, a number of abrupt changes in the oxygen isotopic composition of precipitation, so delta O18 of precipitation, are documented. The most dramatic of these events occurred 4,000 years ago, when over the course of approximately a decade, just a decade, isotopic values abruptly rose above any seen during the early to mid-Holocene and remained at this anomalous state for almost 2 centuries. We have already seen this when we talked about the Mohenjo-Daro-Harappa culture. This event occurs nearly synchronously with climate changes documented in a number of proxy records across North Africa, the Middle East, the Tibetan Plateau, Southern Europe, and North America. So it's a pan-tropical signal. We hypothesized that the excursion could represent a shift towards an earlier Indian monsoon withdrawal, or a general decline in the total amount of monsoon precipitation. The new record provides a very significant advance with respect to age control and sample resolution of terrestrial climate change over South Asia during this period, when a number of major societal changes occurred. While evidence of a causal relationship between climate and the reorganization of Indus Valley and Old Kingdom Nile civilizations is beyond the scope of this study, environmental determinism is something we talked about before. The tight age constraint of the record show with a high degree of certainty that much of the documented deurbanization of the Indus Valley at 3.9 kiloyear before present occurred after multiple decades of a shift in the monsoon character, but before the monsoon returned to its previous mid-Holocene state. So this corresponds also to the discussion we had about whether societies collapse or they try to innovate and deal with rainfall droughts, and then slowly decline. Okay. Finally, greening of Sahara suppressed ENSO activity during the mid-Holocene. To re-emphasize the idea of what happened to ENSO duration, frequency, and intensity during the Holocene is still kind of a open question, because evidences tend to be from one location or the other, which don't necessarily represent the resolution that is needed to infer these things. Nonetheless, the evolution of the El Niño Southern Oscillation during the Holocene remains uncertain. In particular, a host of new paleoclimate records suggest that ENSO internal variability or other external forcings may have dwarfed the fairly modest ENSO response to precessional insolation changes simulated in climate models. Internal variability just means that the ocean-atmosphere interactions and the nonlinearities along with the land response may create changes in ENSO that are not related to any external forcing like orbital forcing or human activities, for example. Here, using fully coupled ocean-atmosphere model simulations, we show that accounting for a vegetated and less dusty Sahara during the mid-Holocene relative to pre-industrial climate can reduce ENSO variability by 25%, more than twice the decrease obtained using orbital forcing alone. So orbital forcing decreases ENSO variability, but the greening Sahara and associated dust changes double that weakening. We identify changes in tropical Atlantic mean state and variability caused by the momentous strengthening of the West African monsoon as critical factors in amplifying ENSO's response to insolation forcing through changes in the Walker circulation. Our results thus suggest that potential changes in the West African monsoon due to anthropogenic warming may influence ENSO variability in the future as well. So keep that in mind, that paleoclimate does offer some ideas for the future, and ENSO changes, monsoon response to Sahara changes, and Sahara response to orbital forcing and global warming, etc., tropical cyclone changes. They're all kind of related to each other. So these are kind of the Holocene teleconnections induced by orbital forcing and then amplified by internal feedbacks, vegetation, dust, monsoon feedbacks, Walker circulation shifts, and so on, are of relevance for where we are headed in the 21st century as well. Okay.